Hello and welcome to my presentation. My name is Seyyed Amir Ehsan Musavi. This presentation prepared in Memorial University of Newfoundland. The title of this project is Standalone Microgrid Research and Development for Newfoundland and Labrador's Change Islands. This is the final project for Electrical Power Systems course. The instructor of this course is Dr. Mohsen Jamil. Depending on where the remote community is situated, different challenges may arise, but the common would be lack of local grid infrastructure or sufficient grid infrastructure regularly poses a significant problem for remote communities. Transportation and access challenges are common amongst remote communities also. System design also be really challenging. It is a well-known fact that some renewable technologies are variable, like wind and solar, and they cannot guarantee a constant supply. The remoteness of some community generation assets can also encounter challenges relating to access to routine maintenance and increased cost of maintenance, ultimately impacting upon project performance. Last but not least is the project financing. To transfer the electricity to remote area and islands, it's gonna be really difficult, and also it's gonna be really expensive to transfer the wires underwater and kind of that to transfer the power, and also we have power losses through the grid. Also, it's really difficult to transfer the power by underwater cables because it's difficult to establish this grid, and also it's really expensive and pricey. And the maintenance is something different from the normal grid because it needs a lot of equipments and divers, and it's gonna be really pricey. Except preparing energy from renewable resources, we have two options for preparing electricity for remote areas. One of them is grid extension, and another one is diesel generators. The remote area power solution which I'm looking for in this project is off-grid power system. This is consists of wind energy, solar energy, and other generations like hydro, and battery energy management and integration, and also controllable load. It needs to be mentioned that it's not connected to the national grid. Components of microgrid system are the solar energy, I mean solar panels, which able us to get the energy from the sun. It's unlimited energy. It's a clean energy, and also the wind energy, which it's the ability to get the energy from the wind through wind turbines, and it's also unlimited energy. And we need energy storage section because we can storage the surplus energy in it. And also we need diesel generator for the smart grid because sometimes we cannot prepare the enough energy and meet the energy demand of the grid, so we need diesel generator to help us. In this project, I'm designing a smart grid for the Change Island. This island is consists of two parts, north and south. It's located in Newfoundland and Labrador between Notre Dame Bay and the Labrador Sea. The total land area of this island is 5.36 square kilometer, and also it is hosting approximately 184 residents. This bar chart shows us the energy demand of this island. As you can see, mostly we need more energy on November, December, February, and January during a year. And approximately for each day, we need 3.95 kilowatt hour energy. So for 184 residents, we need 728 kilowatt hour per day energy. In this section, I am discussing about the renewable energy potential of Change Island. On the left bar chart, you can see the solar energy potential for the island. As you can see in the bar chart, the maximum daily radiation is for June and July, which is 0.46 kilowatt hour per square meter per day. And in the right bar chart, you can see the wind energy potential for the Change Island. And as you can see, we can get more wind energy on December and January, which is approximately 11 meter per second. The software I am using for this project is Homer. Homer stands for Hybrid Optimization Model for Electric Renewables. With this software, I'm trying to find the best model for providing consumers with cost-effective power. This is the system architecture of this smart grid. The system design based on the resources that I explained, which are accessible at the given location. The setup of the system is intended to operate independently without any connection to the power grid. The delivery of the necessary amount of energy for this particular location at the lowest possible MPC and COE. The wind turbine system which is chosen for this project is Bergerie XL6. This rated power is 5.5 kilowatt at 11 meter per second wind speed, and also peak power is 6.2 kilowatt. And the annual energy it can produce it's 9,920 kilowatt hour at average 5 meter per second wind speed. This line graph shows us the relation between output power and wind speed. As you can see, after uh, 12 meter per second wind speed, there is no big difference in the power output. The photovoltaic system we are using in this project is SPRX21. The specification of this kind of photovoltaic system can be seen in this table. The average panel efficiency is 21%, which is really good. And the rated voltage is 57.3 volt. And the maximum system voltage is 600 volt UL. This line graph shows us the solar power output during a year. As you can see, we can get solar energy all days of a year, and the maximum of that is about 110 kilowatt power energy. In this slide, I'm going to introduce the diesel generator used in this project. In terms of emissions and CO, it produces 16.5 gram per liter fuel. And in terms of fuel properties, the lower heating value is 43.2 megajoule per kilogram. This line chart also shows that it can produce power depends on the fuel consumption it receives. So it can produce 170 kilowatt when it receives 45 liter per hour fuel. Battery also using for this project is introduced in this section. In this line chart, you can see the daily energy content of battery, which shows in this line chart during a year, and also you can see the daily maximum charge power of this battery. This battery is Enersys PowerSafe SPS C11. For this project, also we need an inverter. Uh, you can see the shape of this inverter and also efficiency graph. It means that in this line graph, whenever it has 30% output power, it can have efficiency between 96 to 97%. And also in this table, we can see the inventor specifications. For example, its model is X3001 and the maximum power is 3000 volt and nominal AC output is 240 VAC and input and max AC current is 13 ampere. After this slide, I'm going to show you the result and discussion of this project. You can see in this table the cost of the components I introduced you in the previous sections. You can see the first one is converter. Its model is Pico Grid Tie Hybrid X3001. Its price is $2,800 per 3 kilowatt. And for the wind turbine, its model is Berger XL6, which is $5,700 per 6 kilowatt. And also for battery, its name is Enersys PowerSafe SPS C11. Its price is $300 per 1.34 kilowatt hour. And for solar PV system, its name is SunPower X21 BLK, and its price is $75 per 0.335 kilowatt. And the diesel generator, I introduced that one also in the previous section. Its price is $1,200 and it is auto-sized. After inputting previous informations in Homer software and rendering, I got these solutions, the best three solutions. The first one consists of PV solar panels, wind turbine, battery, and converter. Its COE, which means the cost of energy per kilowatt hour, is 0.169, and MPC is the total amount of money we need to pay is 1.12 million dollars, and initial capital for this solution is 473 and $795. The renewable fraction of this solution is 100%, and we don't have any annual fuel because we don't have a diesel generator. The second solution consists of PV panels and wind turbine, diesel generator, battery, and converter. It has 0.187 dollars per kilowatt hour, and its total energy, it means total financial budget we need is $1.24 million, and its initial capital is $674.182, Its renewable energy fraction is 99.8%, and its annual fuel it needs is 148 liter per year. The third solution consists of only wind turbine, battery, and converter. Its COE is $0.191 per kilowatt hour. Its NPC is $1.27 million, and its initial capital is 588 and 159 dollars. Its renewable fraction is 100%, because it doesn't have any diesel generator. In the four following slides, I'm gonna compare the solutions together. Uh, the first one shows us the cost of energy per kilowatt hour for each solution. So the best one is the first solution, which consists of PV panels, wind, battery, and converter. Its cost of energy is less than 0.17 US dollars per kilowatt hour. And the worst one is the third solution, which is more than 0.19 US dollars per kilowatt hour. This bar chart also shows us the NPC of three solutions we have. It means all costs that the system incur over the lifetime. The best one and cheapest one is the first solution, which consists of PV panels, wind, battery, and converter. And the worst one is consists of the wind, battery, and converter, which is $1.25 million. All the costs it has over their lifetime. The next bar chart shows us the initial capital for each solution. You can see still the first one, which is consist of PV, wind turbine, and battery and converter, is the best one and the cheapest one. It's lower than $500,000. So still the first solution is the best solution. This bar chart also shows us the renewable energy fraction in each of the solutions. Obviously, we have 100% renewable energy fraction for the first and third solution, and only we have 99.8% renewable fraction in the second solution, because in the second solution we use diesel generator and we need fuel, so we have CO2 emission. Thank you for your attention to my presentation, and also I'm gonna thank to Dr. Mohsen Jabil about this useful course we have in this semester in Memorial University.